Garrett, and this is my physics lab 2. So just a quick introduction. The purpose of this lab was to determine the amount of charge evenly distributed across one piece of tape needed to make another piece of tape float. And just for a quick preview of results, the charges that we got from labs 1 and 2 were both different. The charge from lab 1 was 1.4 e to the negative eighth. From lab 2, it was 2.4 e to the negative eighth, so it doubled between those two. Now the electrical force in these two labs was the same. It was 1.9 e to the negative third for both of these labs right here. And we'll talk a bit more about that in a little bit. Just to go over some quick fundamental physics topics, we use Coulomb's law a lot in this lab. It's just the force between two charged objects, and this force could lead to attraction or repulsion just based on what exactly the charges are. So if they're both positive or negative, then they will repel, and if they're different charges, opposite charges, then they will attract to each other. And you can see the formula for that right down here. For the gravitational force, excuse me, yeah, we use gravitational force as well, which is just Earth's natural pull that'll attract objects toward each other, and that is based on Newton's second law, force equals mass times acceleration. And we just modify it a little bit. We just say force of gravity is equal to mass times gravity because gravity is what's doing the acceleration. So our observed model is the exact same as lab 1. As you can see the picture here of us trying to float the two tapes up with one another. Just a really simplified model of what's going on in this above picture right here. Two tapes being separated by distance d and being able to float on each other. And then our initial values, we had to calculate out the mass. And for the mass, we calculated 0.0002 kilograms. And then our length was zero point 0.2 meters and our width was 0.02 meters. And these were both measured values. And our system was tape B because that's what we're trying to find the charge on, what we're trying to find the force on. And our environment, or excuse me, our surroundings is tape A in the environment. So the environment being the lab room. Everything that's not tape B counts as the environment. As you can see here, the calculations done right here to determine the charge of the tape and the just the charge on that tape B. For our computational model, this was much different. It's much more complicated because now we're not using point charges for these two tapes anymore. So you can see the formula for electric field. It's the exact same as the one that we used in lab 1, but when we get down to line charge, this is just making the, defining what exactly the charge is going to be on these two pieces of tape right here. So as you can see, we've got the starting axis and the position and whatnot. And then down here, this is where we start making the spheres. These spheres each represent charges on the tape. And these are what's really going to be doing the heavy lifting in this section right here, because these charges are what we're approximating the charge of the tape as. Now, for right here, the second block, this right here is us trying to find, the field of the tape, the field of the electric tapes due to each other. So as you can see, we have the electric field at the location of the top tape due to the bottom tape right here, and then electric force on the top tape due to the bottom tape. And this is just us trying to figure out what exactly the field and force is due to the charge on that tape that we charged up. Oh, and then this last part right here, this is just calculating the net electric force and gravitational force. So this is just us saying, arrows, we're representing the net electric force using these arrows that we've made in the previous section. We're making an electric force vector arrow, gravitational force vector arrow, and that's just supposed to show the magnitudes of the electric force and the gravitational force. So this is the computational model right here. This is the results of it. As you can see, we have all those arrows representing the charge tape. Then we have the magnitude of the electric force. And then we have the magnitude of gravitational force. And as you can see, these basically even out, which keeps the tape from either rising or falling. So this lab was pretty similar to lab 1 in the sense that we had to find the magnitude of charge required to float one piece of tape up using another charged piece. But in lab 1, all we did was approximate these two as point charges. And in lab 2, we actually treated them as strips of charge spread out over the surface of them, which makes these precisions much more precise. Calculations much more precise, excuse me. And just some assumptions and sources of error that we need to go over. So we assumed air resistance was negligent and didn't need to calculate it. And we also assumed that each tape had the exact same amount of charge evenly distributed across the surface, um, which may or may not have been true. But for our percentile sources of error, these are the exact same as lab 1, just the tape grazing our hands and other surfaces during the experiment. The tape mass was calculated, not measured, so that could result in some discrepancies. And then the room humidity also could have affected how great the charge was and how it affected the other tapes movement as well. And then as well with modeling tapes as a point charge, this is what we did in lab one. It just results in much less precise values because we're not we're not as accurately representing the charge that's being spread over the tape. We're just using one single point charge. So that's why over here, when we're discussing the differences in accuracy, I would say the lab two is more accurate than lab one because there's more precision in the modeling of the tape in lab two than there is in lab one because we're representing that charge as a strip of charge instead of just a single point charge. And that's the end of the video. Thank you.